In this video, we're going to go through a couple more simple transfer functions to help be building blocks for our more complicated transfer functions. The first one that we're going to do is the single pole again. It's just written in a slightly different way, but it's written in a way that we will use more often. So typically when we factor our denominator polynomial, we get terms s plus a, where minus a is the pole. So if you go through the same analysis that we did, you get an expression that of course is very similar, structured just a little bit differently, with the idea that when we start sketching this out at small omega values, you get a value that looks like minus 10 log of a squared, so minus 20 log a. And so that is not necessarily a zero value. So if a is 1, then that does indeed become 0 dB. But if a is smaller, then that becomes positive because the log is then negative. Or if a is bigger than 1, then you get a negative decimal value. So what that's ultimately doing is it's shifting that kind of y-intercept value based on what the value of the pole is. Again, at large values, you get minus 20 dB per decade, just like we did before, because then at that point in time, omega is larger than a. And so again, that breakpoint is around when omega is equal to a. So this breakpoint for a being 0.1 is indeed when omega is at about 0.1, and at a is equal to 1, that happens at omega is equal to 1, and so on. So that breakpoint keeps shifting to the right. And so it's a different way of visualizing essentially the same Bode plot, but this y-intercept change does affect it. The phase diagram looks almost identical. The only difference is the breakpoint happens where omega is equal to a, but otherwise it is a phase delay starting at 0 at small frequencies and ultimately yielding minus 90 at high frequencies. So it's a consistent refrain that a pole, so 1 over s, or 1 over s plus a, or our other version of our pole that we had before, leads to a phase lag. And so that's indicated by this minus 90. So all the phase, you lose phase by adding a pole. And the opposite is true, what we're going to see next, which is this corresponding 0, s plus a, you always gain phase. So as promised, we're going to do now the 0, the corresponding 0 there. And so again, essentially, you can either solve this out directly or you can use the reciprocal rule. And again, it follows that you flip this plot over this minus 0 dB line and the 0 phase line. And so now the opposite happens. If a is 10, then you're amplifying, and if a is 0.1, you're smaller than 1, then you're diminishing the magnitude, so the magnitude gets smaller. And again, be thinking about the fact that you've got a sinusoid coming into a block that gets characterized by g, and what comes out. And what we're doing is we're characterizing how big that phase is and and how far shifted that phase is. In this case, in here, we're amplifying, so this output is bigger than the input. When it's at minus 20, then this output is smaller than the input. And so that's really what you observed in lab 2, and that's hopefully what you're able to visualize when you're seeing these Bode diagrams. Like we were saying on the last slide, a 0, no matter how it appears, whether it's s or s plus a or tau s plus 1, we are going to get a phase advance. So as you increase frequency, you're going to add phase. And so you're either going to add 0 or some positive number of phase. And so the pole and the 0 act in different and opposite ways. The next modular building block is when you have a set of complex poles. And so in that case, the complex poles need to be characterized by a quadratic. in the denominator. And so you can compare this to our conventional second order system. There we didn't use omega 0, we used omega n, but effectively those mean the same thing, just different notation. So I'm going to skip going through all the math because I think that it becomes rather challenging to kind of even be able to sketch based on this particular end result. So so you can go through that. That's a good practice if you want to practice it. But ultimately, we get plots that look like this for second order systems. You start at 0 dB at low frequencies. At low frequencies, you're not changing the amplitude of that sinusoidal signal, and you're not changing the phase. Because it's a pole, and in fact a pair of poles, you're going to be losing phase, so it's going to be a phase lag. And one of the important things is this ends up becoming, because you have two poles down there, you're going to get a total phase lag of twice minus 90. So you get minus 90 due to one of the poles, and minus 90 again due to the other pole. So both of those factor in, so overall you get this negative 180 over the course of the entire frequency interval. In the magnitude plot, eventually this is going down, and this is going to be going down again because you have two poles. Even though they're complex conjugates of each other, there are two poles. So you're going to be going down at 40 dB per decade. And so that's going to characterize this as a steeper slope than you'd get by a single pole. And then finally, at the transition point, this transition point happens at this omega 0 value. So when omega is comparable to omega 0, so in this case omega 0 is 1, so at that point these omega and omega 0 are comparable, you get the transition in the phase. So that's kind of this halfway point in the phase transition. But then you also get this resonant peak in the magnitude plot. And so this resonant peak is really characterized or determined based on this damping value. We talked about the zeta parameter as being a damping value. And so as damping gets stronger, so essentially it's a thicker system, more resistance, more damping, you don't get this resonant peak. This resonant peak doesn't appear. Instead, you get this kind of smooth transition. But as the system has less and less damping, then you can get this amplification that happens when omega is close to omega 0. And so that's what characterizes a complex pair of poles as a transfer function. So now we can take a look at the comparable, where you have a complex zero, a pair of complex zeros. And so there you've got essentially things in the numerator that are complex valued. And again, we're going to use that trick where we essentially flip the Bode diagrams over the 0 dB and the 0 phase. And again, because it's a 0, we anticipate that we're going to get this phase advance. And because it's 2, we get the 180. And then similarly, we start out at 0 and we go up at 40 dB per decade, and there is this resonant, it's a peak still, but it's a peak that essentially indicates a dip in magnitude due to that 0. And so we'll be able to interpret that in a couple of ways once we get a little further in the course. And again, the damping kind of reduces that offset. One of the things that we can look at in a different plot is if we keep the same damping ratio, but we change that omega 0 value, like we said, that transition happens at omega 0. So as omega 0 gets larger, that transitionary point, essentially here, here, and here, moves to the right. So that happens when omega is close to omega 0.